My warm welcome to all of you who have joined us. This is the International Workshop on Nanotechnology for a Sustainable Energy, and we are at session 5, Resource Management and the Circular Economy, addressing UN SDGs 6, 7, 11, 12, 13, and 17. And my name is Jatin Nathwani. I'm a professor here at University of Waterloo in the Department of Management Science and Civil and Environmental Engineering, and I'm also the Executive Director of the Waterloo Institute for Sustainable Energy. Welcome to all of you, and thank you for joining us. And without much further ado, we'll simply get started with the session. Our first speaker today in this session is Professor Karin Schroen, Professor of Food Process Engineering at the Wageningen University in the Netherlands, and her subject will be nano for agriculture or food. Professor Karin, please.
Thank you very much for the nice introduction. It's really my pleasure to talk to you today about what I see happening in terms of applications of nanotech in agriculture and in food. And I've also taken the liberty to even take you a little bit further and talk about the future developments that I expect to happen. As you can also see on the slide, this is the Wageningen layout for slides, but you also see the University of Twente. At the bottom right, I have two professorships. In Wageningen, I work on food process engineering, and in Twente, I work on membrane separation, also for food. And that comes actually very nicely together when we talk about nanotechnology. So, yes, it was about sustainable development goals, so I've decided to just bring all of them. Actually, I want to point out that food and food production is actually related to just about any of these sustainable development goals that you can come up with. Even if I have gender equality, access to healthy and also relatively cheap food is very much an issue there. And that also means that if we can do something in terms of food production, and then you can think of like increased productivity, but also in terms of much more healthy foods, we can really make a huge impact if we get food right. And for that, I see a big role for nanotechnology, also nanotechnology as it's currently applied in sensors, and also microtechnology. I will come to that back later. Now, about nanotech, what can we expect from it? Well, first of all, much better control over the production of foods. I'm not sure if you're aware, but just about any food that is processed in a company will get a heat treatment. And the more precise we can apply this heat treatment, the less damage we're going to be causing to the food as well, and the higher the quality can remain, while at the same time not sacrificing on safety of the food, because that is, of course, a requirement. That is something that always needs to be met. But highly specialized sensors and basically system control can really improve the quality of the food as we know it. The food as such is, of course, a big thing, but you can also think about the production of raw materials. Also there, a lot of progress can be made thanks to better use of smart technologies. I mean, there's a lot of products around that we don't even consider as food. So I've brought you an example here on the top left. That's a sugar beet, just in case you don't recognize it, but it's a sugar beet. And we like the stuff that is like in the ground, but the green stuff that is on top, we basically put back in the land. But it also contains a lot of very valuable protein that could be used. It's Rubisca, and that is that could be a very useful source of proteins. I will come back to the importance of proteins later, and then it also makes sense that I'm looking at alternative sources here. The image that you see here on the right top is microalgae. Also, microalgae can be a potential source of new proteins. But of course, we would need to have everything separated and also accepted in society, which is not so trivial. Then, what else can we expect? Well, basically, if we have better control on all these processes, it will cost us much less energy and also much less water. And both are really impactful in the world as we live in at the moment. And my fifth bullet point here is also quite important. I think we can really contribute to longer shelf life of foods. And that immediately translates to less food waste. And since we're basically wasting 1/3 or so of the food as we produce it, big steps could be made if we can do something about that. What else? I think we can make much better use of the relation between food composition and also health effects that are that can be created. The top left, well, the one in the middle on the left, that is actually milk. And if we could make we could make milk more healthy, for example, by doing the trick which is right underneath it. That's a double emulsion. So we could take away part of the caloric weight from milk droplets, from the fat droplets, replacing it by a water phase on the inside, and also dope that with vitamins. I know that doesn't sound very tasty, maybe, but it would really reduce the caloric weight, and it could also really increase the vitamin or the mineral content of foods. And many places in the world, that is still an issue. So what do I think? Just to wrap it up in one nice sentence, if I think about technology and food, it's not just from farm to fork, which we can really improve, but it's really much, much more and much more impactful. So let's start with the production of food on the farm. If you would have asked farmers 10 years ago in the Netherlands whether they would be owning a drone, most probably not many of them would even have heard about a drone. Nowadays, every farmer has a drone, and they use it with really nice results. So they use it to monitor the quality of the soil. They dose the growth media in very specific ways. And it really leads to much higher yields on the land. It's also used to check on the storage conditions and how that relates to the quality of the stored material there. It's even used to much more intense levels if you think about these vertical farms. In the Netherlands, nowadays, we're building vertical farms where, and you see an image here on the right, where technology really plays an incredible important role, and that is in water supply, nutrient supply. A lot of very high-tech solutions are used to make our food, and yes, it is less energy intensive, it is less water using. So in that sense, really big progress is already underway at this very moment as we speak. So in principle, I think that we are able to get more out of less if we go in this direction. Now, let me also address the point of processing of food, packaging, and also waste prevention. Also there, a lot of developments take place. In principle, a sensor could be put on just about any food package, and it would record the temperature that it goes through, and that is immediately linked to the safety of the food. So again, here we can really make a lot of progress. Packaging in combination with sensors will really reduce the amount of food waste. This is a Dutch picture, but it says like 1/3 of the food is being wasted. And of course, I feel that that is a really terrible thing to happen in the Western world. while in other parts of the world people are dying from hunger. That simply doesn't go well with me. Then, for example, having these kinds of relatively simple sensors on a package would really be a way out. I just took an example. There's many around there. This little red sensor in the front, basically it changes color depending on the ethylene concentration in the gas. And ethylene is related to the ripeness of the fruit that's inside. So in that way, a consumer would buy a package and know what the quality is of the product inside, and also till what time it can be safely consumed. So again, I think that would be a really big step forward. Now, a real big point at the moment in food production, and that has to do with protein. Of course, protein is very important for growth and building muscles. And in, especially in the Netherlands, of course, we use a lot of dairy proteins and also animal proteins. That is in our daily diet. But the only thing is that by doing so, we really are not very sustainable. In the left graph here, you see that in order to make a kilogram of cow's protein, we basically need to feed the cow 7 kilograms of plant protein. This is not like an absolute number. You will see different numbers in literature. But the main message is that in order to make animal protein, you need to put in way much more plant protein. And it would make absolute sense, especially if you look at the image on the right, that we would simply eat these proteins directly. And I like it. I mean, I love Indian curries, that kind of stuff. I mean, it's wonderful food, so there's nothing wrong with it. But still, not that many people in a Western society would immediately be very enthusiastic about it. They don't know what they're missing, by the way. And these protein sources, they can also be used as ingredients, of course. But the big question is, how functional are they? Can we simply say, like, okay, dairy protein, let's replace it by plant protein, and that's it? Well, no, of course not. So what I've done in my lab is develop all kinds of tests, so small tools, with which I can look at functionality of different proteins. And I've used like microfluidics for that. And I'm going to show you just one example, because I didn't really want it to make it too intensive. So this is about making small oil droplets. And in just about every food, there are small oil droplets, and you want to keep them stable, because otherwise you have like a pool of oil sitting on top of your product, which wouldn't be acceptable. Now, in this, I will start the movie. So droplets are coming from the top and the bottom, and you see that they meet each other here in this wider channel. Now, the movie is slowed down an awful lot, but you see that they, well, basically they go and meet and greet each other, and sometimes they like each other so much that they actually merge. Now, from a food perspective, that is not the good news. If they merge, then basically the product is not stable. But in doing these experiments, I can very fast get an impression on how well a certain alternative food source works. And the nice thing about it is that I can analyze things at very short time scales, sub-milliseconds, and that is very close to the time scales that would also be applied in industry. So I'm getting very close to, let's say, simulating the conditions as they also would occur on larger scale. That was just one example of what we do. We can also use nanoparticles to make emulsions physically stable. On the right here, you see solid fat particles that we have made, and these solid fat particles, they would also occur in cream, for example. Now, what we've done is make two different emulsions. In one emulsion, that is the top one, we put antioxidant in the oil, and then we stabilized it physically using these particles. In the bottom one, what we've done is add the antioxidant to the particle and then stabilize the emulsion. And if you then look at the oxidative stability, which is on the left graph, you see that the one that has the antioxidant in the particles is very much slower in oxidation than the top one. And that has to do with the fact that oxidation is initiated at the interface, and because of the use of particles, we put them exactly where they can be most effective. So this is, again, a nice application of nanotechnology that really helps increase the food quality. I think we can even push it much further, because making a food in a very stable way, that is, of course, really nice. But the digestion of the food is also really important. And also there, microfluidic techniques have been used. You see an example here on the left from INRA in France, where they captured small oil droplets, and you see that they just digest within an hour. And that is not completely what we wanted at that time. We wanted it to stay a little bit longer, about 2 hours, because if we can do that, then the oil reaches the very lower part of our intestine. And if it reaches there, then basically we can use it to, like in a weight control strategy, because if oil reaches the lower part of the intestine, you get a signal back to your brain that you have to stop eating. So basically you can fool your own body and use a small food ingredient. I mean, it's really not big, in a weight control strategy. And also that is a nice way of using nanotech and microtech. Well, I mean, the sky is the limit. Nowadays, we see a lot of developments in organs on a chip. That is in a pharma field, for sure. But it's developing very rapidly. And if it can be done for pharma, in principle, I think even food is our best medicine ever. So it could even be tested on organs, possibly even like on personal cells. And in that way, you could really go from a technical functionality to a digestive functionality and even to personal health. Yes, I know it sounds extremely futuristic, but I do feel that these are options that will be with us within not too long. And the great thing, if we could achieve that, is that we could help consumers to eat themselves healthy. And I think it would add really years, healthy years, to a person's life if we could achieve that. Yes, very futuristic, but I'm also a very optimistic person. Okay, just to wrap up, the advances in food production in terms of nanotech, I see a lot of applications popping up now, whether it's in the field, greenhouse, food factory, in the consumer. It's happening. It's there. It's out there, and I'm very excited about that as well. I'm possibly even more excited about the fact that I can even bring it to the next level, as I just described, and really link to health and also to sustainability. Now, having said that, I want to wrap up with my final message, saying that nano and also microtechnology, whether that's in sensors or as standalone technology, is going to be really instrumental in supplying the food for the world that also future generations need to live in with sufficient and also healthy food. It's really a new perspective on a sustainable world, and I hope that you're just as enthusiastic as I am. Thank you for your attention, and if you have any questions, then I hope that there is still time to take one.
Thank you, Professor Schroen. It was a very helpful and hopeful and a positive talk. I certainly enjoyed your remarks, and I will now call upon Professor Guus Rijinders. He is co-scientific director MESA and chair of Nano Lab in the Netherlands. And the title of his talk is Nanomaterials for Energy and Sustainability and Nano LNBN Lab NL Facilities. Professor Rijinders, please.
Thank you very much. So what I want to do in this presentation to show some slides on our NanoLab NL facilities and then move to nanomaterials for energy and sustainability. And actually, this is mainly the work on batteries that's being done in the group of Mark Hyben, and on solar energy in the group of Monica Morales. So, well, let's start on Nanolab NL. This is our national facility for nanofabrication that is on 5 locations. And you see it here on the map of the Netherlands. So it parts are in Groningen, in Amsterdam, Delft, Eindhoven, and in Twente. And we offer, let's say, nanofabrication tools for research, for development, prototyping, and small volume production. So later on, you also see that also companies and startups are using these facilities. So at every location, you have most of the basic infrastructure needed for nanotechnologies such as lithography tools or deposition tools, etching tools. But on at specific location, we have also expert techniques. For instance, on nano imprint lithography and others. So, and actually, we wanted to set up this consortium in such a way that we can invest heavily in nanotechnology tools, but not have everything or every tool in every lab. A little bit about the history. So it started in around 2004 as a special flagship of NanoNet, and NanoNet was a initiative to form a consortium on nanotechnology. It was mainly let's say groups from universities, and Philips was heavily involved in that. We continued Nanolab NL when NanoNext NL was formed, and I think you already heard from Professor Albert van den Berg already about NanoNext NL. And now we have Nano for Society, and we want to continue investing in these nanolab equipment. And actually, at the moment, we applied for a special instrument of the Dutch government to have dedicated equipment for quantum technology, but can also use for others for quite a lot of money. And let's hope that we will get this application granted. We do a lot of technologies, but if you kind of look at what are the major parts, these is on fluidics, lab on a chip, organ on a chip technologies, on advanced materials, on photonics and integrated photonics, and on quantum technologies. And TU Delft, for instance, is doing more on quantum. Groningen does more on advanced materials. University of Twente and Eindhoven more on photonics. But also in the University of Twente, we do a lot of fluidics. But actually, it's not, every partner does kind of all the 4 corners, but with a little bit, for instance, at the University of Twente, we do a lot of fluidics and advanced materials and photonics. Some facts and figures here. The installed base at the moment is around 250 million. So if you want to keep that up and running, we have to invest, let's say, 10 to 20% every year in it. So it's quite a lot of money. We are able to perform this excellent research, as you can see here from the research grants, for instance, in the European Research Council, and also some Dutch awards were given to nanolab users. On yearly average, we have around 500 PhD projects, around 1,000 publications, and also important that on a yearly average, we have around 6 startups, around 30 patents, and the industrial use is around 20%, and that is direct industrial use, and actually this is rising, so this is increasing at the moment. And also I have to explain here that next to this 20% of direct industrial use, there is also a lot of use in the public-private partnerships. Just to kind of finish up the Nanolab NL facilities, we are also part of the Euro Nanolab. You can see all the partners here, so well distributed over Europe. And at the moment, we are trying to get an S3 status, and this is quite important for political support of the participating countries, but also to get more financial support there. Okay, talking about nanomaterials for energy and sustainability. And this slide shows you the topics that we are working on at our University of Twente. So you can see quite a lot of topics ranging from thermoelectrics, piezoelectrics, thermal insulation, CO2 separation and capture. But you also can see solar cells and batteries. And this is what I want to show a little bit more from now on. So in total, you can say if you connect, let's say, all the research groups that are working on nanomaterials or materials science for energy and sustainability, this is going on in around 20 research groups, where around 60 PhD students and postdocs are involved. Important to mention also that we recently started a Twente Center for Advanced Battery Technology that combines a lot of disciplines that are here at this university, ranging from applied physics, chemistry, electrical engineering, but also engineering technologies. And you can also see that our institutes at the university, so the MESA Institute, the Digital Society Institute, the Twente Safety Campus, and the Fraunhofer Project Center are involved. And we kind of want to connect to a lot of topics that are in this so-called battery value circle. And this is links to safety, to power electronics, to manufacturing, and advanced materials and electrochemistry. And this is what I want to talk about a little bit. This work, particular work of Mark Huiben's group, is mainly done with a very special tool to deposit the material, which is pulse laser deposition. And this is just one of the tools that we have available there to deposit our materials. And the basic idea is that we are able to make model-like materials where we actually can control the atomic stacking, the atomic structure, and so to say, to make model-like materials and study their properties. And just to give you a few examples, so these are cross-section electron microscopy images from very early work already more than 20 years ago on the left, which is a cross-section of a superlattice of our superconducting materials. In the middle, this is an interface between two perovskite materials where we induce a two-dimensional electron gas. And on the right-hand side, you see a structure where we were able to control the magnetic properties. So in the last few decades or so, we tried to push this pulse laser deposition technology in such a way that we are able to control the materials on an atomic scale, so to say. But more important is that in the last few years or so, together with two spin-off companies, there is Twente Solid State Technology, TSST, and Soulmates, we also worked on scaling up these pulse laser deposition tools to larger areas. So typically, these pulse laser deposition tools are used in a lot of laboratories where you typically would deposit materials on a 5 by 5 square millimeter sample or so. But nowadays, with these tools, we can even go up to a 200 millimeter wafer scale. And that is quite promising for getting our materials into production and into real devices. And again, to just show a few examples here. We have this atomic control also on this scale. So we can grow also now, and again, these are cross-section electron microscopy images. We are able to control the growth of these perovskite oxides on top of silicon even, and we have perfect epitaxial growth. For instance, on gallium nitride, so on 3,5 semiconductors, you can see magnesium oxide and a high dielectric PZT compound epitaxially grown on top of that. And even we can grow these materials on top of glass. So we can induce epitaxy also on glassy substrates. And this is, for instance, very important for a few applications like XUV photography tools, etc. So we on these topics we definitely work together with companies on this. Okay, talking about battery technologies. This slide shows you some of the different technologies available in batteries, where you can see on the horizontal axis the specific energy, and on the vertical axis you can see the specific power. And there are a couple of technologies are given there, where you can see this is mainly in black. You can see the lithium-ion batteries. And if you look in blue, you see the all solid-state batteries. And what you actually can see already, this technology pushes the state of art towards higher specific energies and higher specific powers. And actually, what we try to push is to get a technology where you get very high specific power with high specific energy. And that is ideal. So in the group of Mark Huyven, they are looking into many different materials, on anode, cathode materials, but also on the electrolytes. And just to show you an example here, so this is an all oxide solid state cross-section out of that of perovskite materials, where you can see the electrodes and the electrolyte in the middle. And what is very important here is to understand the properties of the individual materials, but more important also the properties of the interfaces between the electrolyte and the electrodes. This is actually a major study now in many projects within this group. And well, we use, of course, state-of-the-art electron microscopies to also understand the crystallinities and also the positions of all the cations and lithium there. One interesting example that is being looked at is again here in the scheme, where you can see the specific energy or the specific power versus the specific energy. You can see that you can well optimize the battery, a thin film battery, for instance, in terms of specific power. So you need a large area. Or in terms of specific energy, you need larger volume of the anodes and the cathode. But if you would have a different geometry, which is called this 3D battery geometry, where you get columnar kind of growth between the anode materials and the electrolytes, you can have both of them. And in the back of this slide, you can see electron micrograph of a surface, where you can clearly see these columns within a matrix. And actually, they were quite successful in growing such mixed materials, such so-called nanocomposites. And here you see also in the cross-section, you can see the electrodes and the electrolyte material actually grown in a single run, and you can get this columnar growth there. So now the next step is to incorporate this in a real battery and see whether you can get indeed high specific power versus specific energies there. Well, to switch gears towards, let's say, solar cell applications, and this is the work done in the research group of Professor Monica Morales. So she's looking, well, for many electro-optical materials, but also halide perovskites for use in solar cells. And actually, she's working on technology based on pulse laser deposition to create these halide perovskites, either by using single source and get these materials working, but also to use a so-called dual laser deposition technique, where you co-evaporate using two lasers, an inorganic material together with an organic material, and on the substrate that this material should assemble into such a halide perovskite material. Actually, well, she did already a lot on the single source growth, and a system that is capable of doing this dual laser deposition is actually being made at this very moment. So hopefully we can show some results on this soon. But just to show some work on this single source deposition of this inorganic halide perovskite, in this case this cesium tin iodide, and this is a quite challenging material because you need to control the oxidation of the tin, but you also should be able to stabilize the right polymorphs, and this should then be done at room temperature. So there are two phases that are possible. The one is a non-optically active material. Obviously, that's not the polymorph that you want to have, but you want to have this black phase, this orthorhombic, the alpha phase that you want to have there. Well, depositions were done using pulse laser deposition, using this single source. And what was quite important also there is that we have a lot of colleagues around in our laboratories that are able to make the right target materials, because if you want to deposit a material using pulse laser deposition, you need to have the right target with the right composition. And this is a process flow starting with cesium iodide and tin iodide, and using the right solid state synthesis and the correct pressing, you can get a single source stoichiometric PLD target. And well, actually that worked out quite well, as you can see over here. So it forms the right phase. So you have this cesium tin iodide in the right structure, as you can see from the right-hand side from the X-ray diffraction patterns, but also you can see that it's well, nanocrystalline, and from the EDX data, where you can see the composition of this material, you can clearly see that the thin film is homogeneously in terms of composition, in terms of the cesium, tin, and the iodide. And then, of course, you have also to check the functional properties here. So this is the absorption coefficient of the material, and which you can see in the plot here, where you see the absorption coefficient versus the energy. And you clearly can see that it is quite different from this metal ammonium lead iodide, and you see a very sharp absorption edge there with the low value of the Urbach energy. So that also tells you that this film quality is quite good, so that you have less defect states in there. So it worked out quite well, and it has been published, as you can see in the reference below. So I need to finish up. My time is up there. So I'd like to summarize here. Well, I hope I've shown you that, that's at the bottom in the summary, that we still have the state-of-the-art facilities in Nanolab NL, and we are continuing and will continue in getting state-of-the-art equipment and keep it as good as possible. And I hope that I've shown you that pulse laser deposition is an excellent tool for atomic scale epitaxial growth of oxides and nano materials, and that we can use them, for instance, for materials that are synthesized with pulse laser deposition for use in photovoltaics and in batteries. And with that, I would like to thank you.
Thank you. Thank you, Professor Rijinders, for your excellent presentation. Linking for us, of course, the extensive range of state-of-the-art facilities in the Netherlands, and the strength of collaboration across different universities, and all working to the fundamental pursuit of fundamental sciences to support development of next generation solutions. Very informative, and I thank you for it. So I'll now look forward to our next speaker. Thank you to Professor Rijinders.
Thank you.
Our next speaker is Professor Goretty Dias. She's professor in the School of Environment, Enterprise and Development, and is of course also a member of Waterloo Institute for Nanotechnology here at University of Waterloo. Her title of her talk is Circularity, Resources, in technology, achieving sustainable development. Professor Goretty, please.
So thank you for having me. My presentation was prepared in collaboration with my colleague Stephen Young, and we're both researchers in the School of Environment, Enterprise and Development, and we're founders of the Waterloo Industrial Ecology Group. My research is mostly in sustainability assessment of food systems and bioenergy, while Steve's research is related to sustainability of critical materials as well as healthcare systems. So we're not nanoscientists, so you're going to be ready for a slightly different presentation right now. So very quickly, I'm going to talk a little bit about some resource concerns, the most pressing resource concerns we have, talk a little bit about sustainability tensions in meeting the SDGs, the need for circularity in designing technology, and finally close off with explaining life cycle assessment and specifically life cycle sustainability assessment for circular nanotechnology. So in terms of resources, we don't have a lot of resource scarcity with some exceptions, but there are many concerns related to the extraction of these resources from political to social and environmental conflicts. The transition to a low carbon economy is driving the need for certain resources, and such as rare earth metals, copper, and cobalt for batteries and components of renewable energy technologies. So we can see here some of the needs that we need more copper, we need cobalt, we need more zinc in order to be able to implement some of these technologies. And at the same time, the supply of these essential minerals and metals is at risk because of the nature of geological reserves. And here we can see that much of the most important minerals and metals that are needed for a lot of our new technology are dominated by a single country. So for example, for rare earth metals, we see China dominates the supply. For platinum, it's South Africa. For cobalt, it's the Democratic Republic of the Congo, or the DRC. And for lithium, it's Australia and Chile. When it comes to biomass production for food and materials, we do have land, soil, and water scarcity problems. We've already taken up 40% of the world's land to grow food. We are degrading soil. We're having water issues for irrigation or just due to climate change. And we have talk of peak phosphorus, which is an essential nutrient for food growth. And we're declining the amounts of phosphate rock that are available. And we're going to have to look to technologies to extract phosphorus from degraded resources such as wastewater. And again, we have the issues of the geopolitics of peak phosphorus in the sense that there's just a few places in the world where we can get phosphate rock, and this creates possible risks in terms of supply. At the same time, although I mentioned that scarcity of most resources is not an issue, the commercially viable resources are declining, so we're looking to things like deep ocean mining and new technologies to extract in ever more challenging environments and extracting lower grade minerals. And we face also social and environmental costs of accessing these lower grade and difficult to mine resources. And there's always been social and ecological conflicts in terms of resource extraction. For example, in the DRC, we have coltan mining is associated with child labor and severe human rights abuses. Habitat destruction and poverty caused by the displacement of the local populations by miners has led to gorillas being killed for food, and populations of gorillas have declined by up to 90% over the last 25 years. So these are just, quick highlights of some issues. There are also ecological distribution conflicts that are associated with unfair access to natural resources by the developed world and unjust burdens of pollution on the developing world. And this is important for remote indigenous communities where most of this extraction is taking place. So for example, Chile has 48% of the world's lithium reserves, and along with the geopolitical risk of having so much of the lithium reserves in one area, we also have the expansion of lithium mining into and causing unwanted transitions for indigenous people in rural areas. For indigenous peoples, these are considered sacred lands, but profit maximization is affecting worker rights and conditions and environmental concerns. In Congo, Peru, for example, there is a gold mine that's been delayed because of the local population is concerned about water supply and contamination for their community. And while they should be, you can see that it's a very common issue to have water contamination. And we can see what happened in the Animas River in Colorado in 2015, when 1 million gallons of wastewater containing lead and arsenic leaked from a gold mine and ended up in this river. This is a difference of 4 days in what happened with that leak. So we can see that the challenges of resource demand for a growing economy, and we have to think about how do we achieve the SDGs. And so there's some clear tensions between development and sustainability. In 2009, Johan Rockström at the Stockholm Resilience Center and 28 international scientists proposed the concept of 9 planetary boundaries that we need to respect if humanity is to continue to develop and thrive without ecological collapse. So we can see here the ecological ceiling for these different boundaries such as climate change, ozone layer depletion, air pollution, and so on. And if we cross these boundaries, we risk tipping points and irreversible global environmental change. We see that 4 of these boundaries are already past the ecological ceiling, and we're seeing this overshoot in these boundaries, which is putting humanity at risk. At the same time, in 2012, Kate Raworth wrote an Oxfam paper called A Safe and Just Space for Humanity. Can we live within the donut being this area here, where she pointed out the need for a minimum amount of resources that would support our society and its social foundation. So how do we supply water, food, health, education for society when we're also falling short on these different parts of the social foundation? So these are the shortfalls. And this illustrates how much of a shortfall we have in these foundations, and in order to meet the shortfall, we need to use resources. But then we're putting the planet at risk. So this is the big problem, and what can we do about it? And you can see here that a lot of these SDGs actually are part of this donut, and we're impacting we're concerned about the SDGs of life on land and life below water and climate change. So part of the solution to living within the donut and achieving SDGs is through circularity and systems thinking. Steve and I are researchers in the field of industrial ecology, which is a systems-based multidisciplinary field that studies material and energy flows. You can see here these material and energy flows through industrial systems and the economy. And we try to understand the impacts on the environment that result from our natural resources and the waste that is produced from production. And we see industrial systems in the economy as having a metabolism in the sense that there's material and energy inputs, and then there's waste is produced. And also we try to use the analogy of natural systems and ecology to try to make products more sustainable. And by trying to mimic nature and trying to do closed loops, dematerializing, or through industrial symbiosis, and also by improving the design of products. The growing metabolism of our society is approaching limits with respect to resource inputs. Between 1970 and 2010, global resource use tripled, and this was driven by population, economic growth, and changing consumption patterns. The material energy inputs are increasing very quickly here and are projected to grow into 2050. But more importantly, what we see is the per capita demand shown by this line is also increasing. So the demand for different types of materials is not just due to population growth, but also lifestyle changes. And this is a challenge of living within the donut. Here you can see how little circularity there is in our global economy. Out of 62 gigatons per year of materials that are reused in the economy, only 4 gigatons are recycled, which is about 6%. This is because almost half of the materials are used to provide energy and they can't be recycled. And then the remaining is, a lot of it ends up in stocks, like in buildings and roads. And so we need to really shift to renewable energy sources and reduce our the society's stock growth and make sure that we're doing eco-design so that we can advance circularity. And in terms of circularity of metals, we're doing pretty well in the mass metals like iron and aluminum. We recycle more than 50%, but in things like the rare earth metals, elements, we're seeing less than 1% recycling, mostly because these are elements that are found in small quantities in things like electronics, and recovering them is extremely difficult because of the small amounts and the design of these systems. So how do we change these trends so we can meet the SDGs? The ultimate aim of a circular economy model is to minimize the extraction of raw materials and waste generation. Some of you may be familiar with this butterfly diagram that was developed by the Ellen MacArthur Foundation. And there's a couple of principles that are implicit in this diagram. The first thing is that we need to manage our resources better in terms of renewable resources and non-renewable or finite resources. And this means regenerating the renewables and substituting materials or trying to reduce them through these closed loop systems. And secondly, you also need to optimize resource use through eco-design of products and services so they're eco-efficient and that we reduce, reuse, and recycle resources both in the biosphere, this biological part, and the technosphere. Now, the problem with cycling materials in the technosphere is that it needs to be part of product and service design. It's hard to do this unless we think about this at the design phase of a product. Also, we have to acknowledge that there's unavoidable losses of material quality as we start to do these circular loops, and that there's also more energy input associated with recycling. So we need to strike a balance between recovery and energy use, or else when we look at a whole system level, there might be negative impacts on the environment. So finally, I want to talk about how to assess sustainability of early stage technology in a way that considers the environmental, social, and economic implications of resource use. So LCA is a systems-based tool. It involves assessing the material and the energy that inputs that go into making a product or providing a service, as well as the emission and waste outputs every step, from the natural resource or the cradle where we extract raw materials, through to transport, manufacturing, packaging and distribution, use and maintenance, and the disposal, to the grade if the product goes to landfill, or cradle to cradle if we can recover the materials. So LC is able to address multiple environmental issues and is useful to ensure that we don't shift problems from one impact to another, so reducing carbon emissions but increasing toxicity, for example, or from one life cycle stage to another. So we might, use, less destructive materials, but later on maybe it means we use more energy. We can do environmental LCA, we can do social LCA and life cycle costing, and we can also combine this with other methods so that we get a full holistic view of a product's or services sustainability. And it's really important is that in the circular economy, every stage of the life cycle of a product or service becomes a design consideration so that we can limit the environmental impact on the environment and the social impact. And just very quickly to explain what I mean by impact. We're able to look at things like climate change, acidification, toxicity, and even we're starting to include circularity in the life cycle assessment and to understand how this affects resource depletion, ecological systems degradation, and human health and welfare. So nanotechnology has a lot of potential for circularity and for making more sustainable products by providing solutions for cleaner production through high precision manufacturing, by using more efficient renewable energy with cleaner materials, remediating environmental damage, and recovering materials such as phosphorus from wastewater. But there have been some preliminary LCA studies that show that producing nanoparticles and some nanotech materials is more energy intensive. So those are one of the things we need to be careful about and need to consider in doing nanotechnology assessment. Also, there are some concerns around exposure and risk pathways of nanomaterials. And this is an area of research that's very new and very needed to properly do sustainability assessment and look at trade-offs. And I know we had one speaker this morning talking a little bit about that. So we need to really assess new nanotechnologies in a holistic way.
Can you please summarize in the next little while?
That was my last one.
Thank you. You did well. Sorry to interrupt. But,
that's okay. No, thank you. I couldn't see the time. So Steve and I have been involved in a lot of technology assessment using LCA, from bioenergy to pharmaceuticals and X-ray machines, and we work with many stakeholders in the supply chain. And there's an incredible opportunity for using LCA for eco-design, which has the goal to protect environmental systems from harm and enhance sustainability of natural resources for the entire product life cycle. And so this eco-design is really perfect for designing sustainability and circular economy aspects into emerging nanotechnology. And it's essential to use at the early stages of technology development so we can avoid locking in technologies that are harmful. One thing that's really important to think about is this design feature, that it's a critical stage of any product life cycle, especially in terms of end of life and sustainability. And 80% of environmental impacts of a product are decided during this stage. Eco-design allows us the design of a product with circular economy principles so we can achieve sustainable and responsible consumption and production. And it requires us to think of how to design for longevity of a product, designing for service, energy efficiency, and dematerialization and a recovery of a product's resources. So it's really important to imagine the final use of even materials that are in the lab design stage, because we can see opportunities and pitfalls and potential applications. We can test different configurations, materials, and build scenarios to imagine different ways of producing the product at different levels, from the components, such as choosing the materials, and to the structure, such as manufacturing and logistics, to the system level and how we look at disassembly and end of life. So finally, the LCA and eco-design framework also allows us for discussion with various stakeholders so we can identify connections and make sure we aren't working in a vacuum. So this is a value of this life cycle approach for looking at sustainability and achieving the SDGs.
Thank you very much.
And that's it. Thank you.
Okay. Thank you. Thank you for a comprehensive discussion of the subject. I believe we will move now to my remarks, which is I'm the next speaker.
Everyone, so I'd like to introduce our next speaker, which is Professor Jatin Nathwani, who is the Executive Director of the Waterloo Institute for Sustainable Energy, WISE, we call it in short form, as well as he is a WIN member. We'll be talking about sustaining a clean energy transition beyond COVID. Jatin, please.
Very good. Thank you. So in my remarks, I will provide a brief perspective on what I call the global challenges and trends that inform the discussion of how do we get to a sustainable clean energy transition. And I'll focus on drivers of a clean energy transition and link it to the relevant scientific and technological innovations that in essence provide optimism even as we struggle to manage the COVID intrusion in our lives right now. Now, COVID, of course, has been a challenge in our capacity to think about the long term, but we need to address the underlying threats that will persist for decades, the threat of climate risk that will shape our lives actually beyond the pandemic. My goal, therefore, is to connect the dots, and I'll thread my way through the challenges of COVID, climate, the urgent need for robust technological developments that pave the path for a global energy transition to a sustainable future. Of course, sustainability requires, in my view, a response that not only deals with the short-term threat of COVID, but also the multiplicity of threats posed by climate risks over the long horizon. I'll highlight some of the scientific and technological innovations and the potential of disruptive solutions that can make a difference, both on the timelines and the scale of change required at the global level to be relevant. So, bending the curve actually is a recent addition to our vocabulary and public discussions brought on by COVID. It's an uncanny resemblance to the notion of bending the curve in the climate change narrative. Intrusion of COVID has at least introduced familiarity of the concepts of exponential growth into the public discourse. Who would have predicted that about 6 or 8 months ago? The common feature here is the notion of risks rising exponentially, and response actions required to bend the curve to limit harmful consequences. Risk mitigation is, of course, all dependent on actions that we take to prevent escalation of dramatic and unacceptable consequences. So between COVID and climate change, only the timescales are different. Weeks for COVID, decades for climate change. And so the image on the right-hand side here is an exposition really of the levels of mitigation necessary to achieve a stabilization of the Earth's climate by 2050 or so. And as it goes, in the case of COVID, no action in the short term leads to high mortality. In the case of climate, no action now leads to extremely high levels of temperatures with the potential of catastrophic consequences of an unpredictable magnitude and scale. Here I show on the left the global carbon dioxide emissions and the corresponding temperature scales, all well-known information that you've seen before. Of course, without mitigation, the red line leads us to an unacceptable increase in global temperatures and into the darker red zone categories of extremely high risks. These are the risks above the blue line. The high risks, of course, relate to destabilization of the Earth's ecosystem, extreme weather events, or unique large-scale disruptions. Modeling of climate impacts dictate essentially a reduction of almost 8 to 9 gigatons of carbon emissions, and that is the challenge that underpins the discussion of targets and strategies for mitigation. COVID mortality impacts also follow an exponential path if mitigation is ineffective, translating into high mortality. This chart here on the left-hand side shows essentially a relentless but steady upward march of the emissions, carbon emissions, decade over decade since the 1970s. Even after 5 comprehensive assessments by the IPCC over the last 3 decades and 25 meetings of the Conference of Parties under the UNFCCC, and now with the Paris Accord, where are we at? In 1990, the share of fossil fuels in the global primary energy supply was 85%. 30 years on, with all the scientific developments highlighting the need for urgent action and political commitment, the share of fossil fuels in the global supply remains stubbornly at 85%. And there is not much time to lose. If we look at the evolution of the characterization of the risk in the IPCC reports from 2001 to about now, abrupt and irreversible change in the climate system have become a higher risk at a lower global average temperatures. The declining lower thresholds are a clear warning sign of a flashing red light. So time for rapid action has arrived, and technological solutions need to be scaled up in a hurry. The extraction of fossil fuels is now no longer a feasible pathway for meeting the global energy supply. It's no longer a question of whether we will have sufficient fossil fuel resources to meet our needs, but the relevant question is whether environmental constraints will allow the use of these resources. So when stacked up against the barriers of meeting stringent temperature limits, whether it's a 1.5 degree target or 1.75 degrees, it's clear that fossil fuel reserves will remain in the ground. They will become stranded assets. Bending the curve to prevent an exponentially driven runaway destabilization of the global climate system means continued extraction of fossil fuel resources on a large scale is literally no longer tenable. Now, of course, a diverse range of disruptive solutions is one part of the answer, but these have to be scalable at a global level. I draw your attention to a number of critical technologies that are part of the toolkit. Now, this I draw from the U.S. Department of Energy report, pointedly observing that the future has arrived for at least 5 energy technologies, all driven by dramatic declines in costs of key energy technologies: wind, solar, PV, batteries, electric vehicles, LEDs, and so on. But I also draw your attention to the 10 or 11 additional what are considered breakthrough technologies identified here. And some colleagues have already earlier commented on this. And they include sensors, devices, all under the banner of IoT, artificial intelligence, machine learning, robotics, energy storage, 3D printing, and others. And these become our building blocks for accelerated change. We have seen dramatic cost reductions over the past 8 to 10 years in LEDs, 95%, distributed photovoltaics, 55–60%, battery costs down 70%, wind generation 40%, and so on. And solar and battery costs continue the path of dramatic declines, and all these are signs of optimism. This one is from the latest International Energy Agency Technology Perspective report, indicating the exponentially decline in costs for solar PV and lithium-ion batteries, for example. The costs have gone down, of course, because of new and innovative manufacturing approaches and adjustments in the technological outputs, but these are supported by robust supply chains and adoption at mass scale. Cumulative installed capacity has doubled almost every 2 to 3 years. So it is becoming increasingly clear, in my view, that the disruption in the transport sector is actually a serious structural shift. Oil will no longer maintain its dominance as a fuel of choice for transport, and the evidence is mounting. Disruptive innovations enabled by digital technologies, data science, a remarkable decline in costs. We've seen 70% within the last 6 years, and electrification of mobility, whether it's cars, trucks, tractors, 2- and 3-wheelers, e-trikes, what have you, pose trouble in essence for the oil sector. I cite one example, speaking of exponential growth. It took 20 years to sell the first 1 million electric vehicles, and then only 18 months to sell the next 1 million, and then 4 months to sell the 5th million. So growth rates of the electric vehicle market, as an example, is projected to double every 2 to 3 years into 2025 and beyond. And this reflects an underlying reality, actually, that customers choose electric vehicles because they offer superior performance and a cost advantage over gasoline cars. And on top of that, with national governments now strengthening policy support by mandating the phase out of gasoline and diesel vehicles, some as early as 2025 and others in the 2025 to 2040 timeframe, the global movement away from the internal combustion engine is now firmly entrenched. And on top of that, the retooling of the factories with massive investments within the auto sector in electric mobility is proceeding essentially on all fronts. Choice of models, longer range performance, expanding charging infrastructure, batteries coupled to higher efficiency electric motors, and so on, showing no signs of decline in cost and performance. And this, I think, is a tectonic shift that will neither be orderly, linear, nor predictable. Okay, so declining costs of the physical components in the energy system is kind of one positive trend in the order of 50% or 70% and so on. But what's even more dramatic is the decline in cost of the components in the ICT sector. Components have to be, of course, integrated into devices and operating systems, and these have to be monitored and controlled for delivering essentially high-quality services. So dramatic declines in cost and performance improvement of sensors and devices, and in this case, at the order of 1,000 times over a fairly short time frame, 5 or 7 years, is, in my view, the bridge to the digital revolution that we talk about and creation of new economic value. So the promise of the digital revolution, when layered on over the physical energy system is a pathway that actually offers some significant hope. Here's a picture that I've drawn and shared over the years, what I call a smart, intelligent energy network that is a convergence of information science and systems with the physical energy system. And herein lies the promise of creation of new economic and social value as ICT becomes ubiquitous through sensors, devices, data analytics, vast amounts of data being turned into useful knowledge and services. So on the left-hand side of the picture here is essentially information flow. In smart energy networks, you've got advanced technology systems that use information from different sources to allow you to make better decisions. On the right-hand side, that's the energy flow, the smart energy network. Linked, of course, different sources of energy, delivery, storage systems, and as a result, you get to smart homes, businesses, institutions can begin to choose the most efficient way to meet their needs for electricity, heating, and cooling requirements, and transport, and so forth. Okay? Now, so what we are really looking at as homes literally becoming virtual power plants. Thinking of your home as a virtual power plant has now become a reality with the help of, again, ICT, sensors, data analytics, remote control, integration of systems, yielding new economic value and returns for the household. This is another example from Germany, Sonnen Smart Grid. The Sonnen Flat Box, for example, connects thousands of battery users and combines many individuals, homes, storages into a giant pool of batteries. This virtual storage, enabled through an intelligent flat box, they call it, is large enough to buffer vast amounts of energy, thereby helping to both stabilize the public power grid. And as a customer, you do not even notice that you're sharing your energy storage with the Sonnen community because the batteries are only used a couple of minutes each day or during a week to buffer the short-term peak power in the power grid. And the aggregated resource can be exploited for, of course, in addition, price arbitrage on the wholesale electricity markets for benefit to the household. So there are multiple benefit streams that emerge enabled by ICT. Here's your car. Begin to think in terms of your car as the ability to control the grid with the development of the vehicle-to-grid technologies, again, fully enabled by sensors and controlling devices and data analytics. Your car becomes an asset as a virtual power plant to the entire power system. So this example was actually proven by a pilot project at the University of Delaware, and the auto sector has really moved into this, what we call the vehicle-to-grid technology as the next step in the evolution. It's not just simply how fast electric mobility displaces the internal combustion engine, but what's emerging is a whole new set of business models characterized as what I call transport as a service or battery as a service. So this moves us away from ownership of an asset to a shared model that reduces capital requirements, improves utilization, and delivers the same service at a much lower cost. Again, the linkage here is, of course, fundamental science as the backbone for new materials, devices, and devices integrated into operating systems, and operating systems optimized for a higher level quality of service at lower cost through digital enablement. Now, of course, there are skeptics, and I like to show this picture. It is looking down Fifth Avenue, New York, 1900 from the Columbus Circle there. And can you see the car anywhere in this picture? This is out of the Library of Congress, this image, and all you have is carriages and horses. Almost within 12 to 13 years, there is no longer the horse. So those who argue that a transition cannot be made fast enough, this is a gentle reminder that when facts converge, things can actually happen fairly quickly. I'll move on to highlighting what I call this is an image of what I call a low carbon energy ecosystem, essentially comprising of four core elements of what I call baseload power, and that's not going to go away anytime soon, smart urbanization, electrified transport, and off-grid electrification for communities that lack access to electricity. All these combining some form of innovative technologies in generation, distribution, and storage to tackle a specific domain within the energy system. And within each element, of course, transformative changes are underway. For example, the global trend towards urbanization actually means smarter urbanization that includes better building design, electrification of transport, distributed resources, renewables on a large scale, and baseload generation as the backbone. Electrification or deep electrification of the economy, aided by the emergence of digitalization, provide, I think, a powerful pathway for decarbonization of large sectors of the economy, including transport and heating for buildings. Digitalization offers a higher level of productive utilization of all these assets, maximizing, in my view, true societal benefit. So we can now begin to see how intelligent energy networks create new opportunities for commercial and industrial enterprises, along with households, to participate actively in energy markets as both producers and consumers of energy. So this is the drift towards electrification that is totally promising. What will it take? Many scenarios have been studied and are under consideration, and I just point to two. What will the transformation to a sustainable future cost? The magnitude of the levels of investment, whether it is you think in terms of planned energy scenario investments or transformative energy systems with slightly different shares and a level of aggressive implementation of some of the low carbon futures, you're looking at anywhere from $3.5 to $4 trillion annual investment globally over a 30-year time frame. And the investment community now is becoming increasingly wary of fossil fuels. Any scenarios you look at, the role of fossil fuels will be largely diminished over time. I'm on my last slide. So I indicated the costs are rise. There are these interrelated global trends that include, very specifically now, the divestment of fossil fuels, securities, disclosure of carbon liabilities, and other mechanisms, all in essence a drive towards transitioning to perhaps stranded assets of these fuels. You may think $3.5 to $4 trillion a year is a large amount of money, but if you put it in context with actual current fossil fuel subsidies, which are in the order of $5 trillion a year, the level of investment is not all that high. Decarbonization can be achieved through diversification of supply, electrification, and digitalization. And even though COVID is there in front of us in terms of it undermining the fiscal capacity of governments to think long term, it's all very clear that the underlying technological trends in the energy transition are all underway, and I remain completely optimistic that we can prevent the large-scale climate risk threats. Thank you.